What's up, guys? This is Heiss, and today we have another 101 video coming at you. I wanted to talk about track. My current day job is being a railroad signal design engineer for light rail and as well commuter rail trains, so I deal with all sorts of fun stuff that I really want to talk about, but in order for you to understand all that fun detailed stuff, we kind of have to go over some of the basics of track. So I figured we would go through really the core concepts of what railroad track is and a lot of different concepts about that. So we may not have 10 levels like we've had in the previous videos, but I thought it would be really important to kind of go over how track works. So let's get right into it. So we're going to start with the basic components of railroad track. So first things first, we have this lovely picture of 491 from the Colorado Railroad Museum, where I used to work. This is one of the locomotives that I help return to service, but we've got some good pictures of track here. In these videos, I like to talk from a very low level so that people who don't really know anything about this stuff can understand. So if you already know some of the basics, everything is chaptered down below for you. Railroad track primarily consists of rails, 2 of them at least, sometimes more, ties that go transverse to the rails or perpendicular to the rails, and then the rails are held to the ties with spikes, and maybe you've seen those in your day-to-day, probably. But equally important as those 3 primary pieces are also the ballast that the track rides on, and then the actual grade that the ballast sits on. So in order to have a railroad, you have to have an actual grade for it to sit on. So you can see that previously, with the way that the geometry of this area looks, there used to be just a smooth path here, but you can see that a wedge-shaped grade has been placed here. And then there's a small amount of ballast on top that actually holds the track in place. But you have to have that foundation in order to have good track. I told a story in one of my earlier videos about this specific curve and this specific locomotive, actually, where because this used to not have good ballast, it was ballasted with dirt from the excavations in a cut that's off to the camera to the right, 491 actually moved this curve at this point 6 feet on center this way and made it quite the kink. It was actually probably a little bit closer to the camera, but it was this part of the railroad. And because the track was not up to a good standard. So we may be talking about really basic things here, but they're actually really critical in the actual construction of a railroad. So obviously we have our rails, we have our ties, we have spikes, ballast, and a grade. Let's talk a little bit more in detail about a couple of those components. Let's talk about rail, shall we? There's a lot of different kinds of rail. Most American rail looks something like this in profile. And here's some important terms for you to know. The top is called the head of the rail. The middle is called the web, and the bottom is called the foot. Those are your 3 basic terms when we refer to anything on the rail. These are really important, so you're going to have to know them as we move forward. That's how the parts of the rail are identified, but another important thing about rail is the actual overall size of the rail, because that has huge implications for the use of the railroad track, how easy the track is to build, and the type of railroad track that you have. So early on in construction of track work and rail manufacturing processes, we could only really make shorter pieces of rail. Over time, the lengths of rails that have been manufactured get longer and longer and longer, and the railroads are using some absurdly long pieces of rail now, but it was pretty common back in the day to have maybe a 21-foot long section of rail or a 30-foot section of rail. There's a lot of great history there for the history nerds out there, but the point is we had shorter pieces of rail that we could transport on a train car so that we could move the rail to the locations where it needed to be installed ahead of the train. And so as such, you had to have multiple joints or segments depending on how long those rail sections were, and you had to work with those pieces. Longer sections are easier to bend without having a kink in the joint. So as things got longer, constructing track got a little bit easier in some ways. These days, the rail is actually welded into longer segments and transported wholly by train, and they're using something like 400-foot long sections of rail. It's kind of absurd, but that way they can minimize the amount of welding in field and minimize the amount of joints that actually need to be put in place. There's another important factor about the size of rail, We talked about the length here. There is a considerably important and also considerably American way to measure the weight of rail, which is the overall size of the rail. It is measured in pounds per yard. So for all of you that are outside the United States, that is pounds for every 3 feet, which ends up becoming something roughly like pounds per meter. And remember, a kilogram is 2.2 pounds. So I'll try and remember to give you guys the conversion on these things. But smaller rails in the olden days were something like 30 pounds per yard or 45 or 50 pounds per yard. And these days we've graduated to primarily using on our main tracks a much taller section and a much larger piece of rail that is 115 or 136 pounds per yard. This is old over here, little small rail, and this is new, big rail. And that was just to deal with the weight of the trains increasing as well, and also to make sure that things are nice and sturdy for higher speed operations. Although back in the day, they did tend to run trains scarily fast on the old, small, not very strong rails. The actual differences in rail manufacturing and rail size actually played a bit of a role in switch design, which we will talk about a little bit more in the switches and special track work video that I'll be doing down the road as well. Okay, so that was a little bit about rails, but now what about the ties that tie them together? Well, if you're in the UK, they're called sleepers, but here in the States, we call them ties. Historically, the ties have been made out of wood, typically oak or other hardwoods, though they tended to use whatever they could get their hands on in some cases. But these days, we also have concrete ties in a lot of applications as well. The ties are usually roughly square in profile, and you typically don't see the edges of them because the ballast is typically tamped down to about the height of the ties themselves as well. But they typically extend quite a bit off either side of the rail to provide support. With the addition of spikes that get driven into the tie, you can hold the rails down to the tie. But one important thing that gets typically overlooked or is not terribly well known by people outside of the industry is that we also have, in most applications, something called a tie plate. And a tie plate is actually a thick metal plate that aligns the rail. It has little feet, and it has holes drilled in it for where the spikes go, so we're not just randomly tossing things in. And it allows for a much stronger bond between the tie and the rail itself. And it also gives a greater bearing surface for the rail to transmit its force through the foot of the rail than through the large tie plate down to the tie. And it also helps reduce some of the wear in the tie itself. So you typically have tie plates, and then the spikes are driven in, and that helps to be a bit more of a more robust system. If I zoom in on this picture of 491 again at the museum, you can see these tie plates sticking out underneath the rail as raised up surfaces all the way down most of these different pieces of track. And again, in the early days, they didn't necessarily have these, but they're quite common these days and considerably important and a great piece of engineering. One important detail to note about the ties that also helps with these tie plates is that typically the ties are treated with a special coating called creosote, and creosote is basically a coal tar that acts as a preservative for the tie to make it last longer in harsh environments, but as well it also acts as a lubricant so that as trains run over, there's less friction and wear into the actual tie surface from any motion or any vibration of the rail and tie plate itself. Obviously, the tie plate gives a larger area, which helps limit the wear, but also adding that creosote also allows for any motion that does happen to affect the tie even less, which results in less maintenance. So that's why the ties are treated with creosote. There's other treatments out there as well, and different things have been tried over the years, but that's pretty much the most common thing. There's another considerably important piece of tech that goes into railroad track that also seems to get lost in many cases, and that is the rail anchor. There are many different varieties of this, but anchors are an incredibly important way to help keep rail in place and also prevent kinks due to temperature. A rail anchor typically looks something along the lines like this. It clips around the foot of the rail and sticks up on the other side typically. And what it does is it prevents the rail from moving longitudinally down the track or up the track because the anchor will rest against the side of the tie. And so that anchor will prevent the rail from moving. So if there's a temperature increase and the rail wants to expand, this helps bear that load and keep it in place. It also helps keep it in place as a train's moving because as the train imparts force onto the rail, either during acceleration or braking, it wants to push the rail one way or another. And with just spikes, you can tend to get a bit of a shear motion going on. But with rail anchors on either side of each tie, or particularly important ties, you can help limit the amount that the rail moves as the train runs over it. Because many trains running over one spot can do a lot of wacky things to the track, as I was talking about earlier with 491. Now, there's another kind of track affixement that is more common to more modern applications, typically using the concrete ties, and that is rather than using the spikes that we've talked about, we also have rail clips. Here are some rail clips in service on very interesting looking track that we'll talk more about in a little bit. These are kind of curly Q little clips that actually hold the rail in place, and they accomplish the task of both the spike and the anchor and help retain the rail down to typically a concrete tie, although in this case, this is what we call direct fixation track, which we will talk about in a little bit. But if you've seen a more modern built railroad or an electrified railroad like this one, you may have seen some things like this. And one last important thing to talk about as far as holding the rails together is something called a gauge bar. And this is a gauge bar. It is a metal bar with threaded rod ends that can be adjusted to put it in place and then grab both sides of the rail. And these can help hold the rail to a precise gauge, because things can work, and as you can see with some of these ties looking a little sad and worn out, a gauge bar in this instance can help hold the rails to the right distance apart so that our trains can run across them. And it's a good way to keep things in check along your railroad. The next important thing to talk about is how we actually fit the different pieces of rail together. So we have two rails here on the left and right, and typically the early way to do it was to use what is called a joint bar. So you would drill 2 holes, 3 holes depending on, in the web of the rail, and then you'd apply a nice flat piece of plate, and then you'd stick some bolts in with some nuts, and I'm using square bolts because, you know, olden day railroad stuff. But this is the earliest way to set things up. You'd have joint bars on either side. Sometimes they're even meshed to fit the profile of the foot and the head so that they sit in place and can't move. You then have the holes drilled, you stick different bolts through, and you can hold your track together. This is the most simple way to fix your track. In modern day, rather than using these, they typically actually do a really, really cool process where they do a thermite weld in the field, welding the 2 pieces of rail together. And so typically, when you have a thermite welded track, the train will end up seeing a continuous piece of rail, just like this, but you'll have an extra bit of thickness right here where the weld was done. And a lot of times, you'll get the welders who are very proud of what they do. They'll typically sign their welds right here. They'll say, yeah, Heiss welded that right there. Boom. So typically, they'll even put that in the side of the rail for fun. But you'll see this extra brick where they'd actually had their welded joint. So the head of the rail is now seamless, so you don't get the bang, 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 bang of the transition across. You have less maintenance, smoother ride, and you're allowed to go faster because of that. This is a much stronger bond than this. But there is still a reason to have these kinds of joints, and that is a special signals purpose. And we'll talk a lot more about these because they're very important in the next video, again talking about special track work and signals. But the important thing to know is that they're called an insulated joint, and it looks just like one of these, except they put a special insulating material in between the rail, and it's really skinny. This is blown up for demonstration's sake. It's actually a quite small gap that they sit in. And as well, the joint bars themselves are also insulated, and so no electrical current can flow from this left rail to this right rail. So there is still a time and place for these, but typically they try to have what is called continuously welded rail, or CWR. So typically you'll see on track drawings, you'll see things like, oh yeah, it's 136 pound CWR through this railroad. Okay, that means that it's 136 pounds every 3 feet, all the way down the railroad, except for when they have to put these in for the signals. So earlier I made a little mention about grade and how important grade is. Well, grade and ballast are incredibly important because we just talked about all this work to make sure that we could keep our rail anchored properly to our ties and transmit the forces of the train into the rail, into the tie, and make sure that things don't move. But if the track itself is not rigidly affixed to the earth, well, guess what? You're going to have a bad time. And again, that's what happened here. In case you didn't see that playthrough video, that was an old Railroads Online video of mine. We were running the other direction, and this is at the top of our hill at the Railroad Museum, where it's about a 3.5% climb all the way up. And right at the top is this curve, and it is a 28-degree curve, which is pretty sharp if you know things about curvature, and if you don't, we're going to go over it in just a minute here. But basically what happened was, without having sufficient ballast, we basically just had dirt or river rock there. The track was slowly pushed over each time we ran over it until there was one critical spot where it basically just turned really hard like that, and you felt it as you ran over it. I mean, the locomotive turned on a dime, and that's not a good feeling. We were running at night, so it was hard to see, but we knew it felt wrong, and something was wrong, so we called the boss to come inspect it and see what was going on. And we crawled through this section of track as slow as we could, and I've never seen the color leave a man's face as fast as it left our boss's face. He gave us the fastest, oh God, stop signal that he possibly could, and we stopped, and we got out, and this is 491, that's the locomotive we were running. It is a 282 Mikado, which means it's got 2 leading wheels, 8 driving wheels, and then 2 trailing wheels. It had picked up its lead wheel on the inside edge of the curve, almost an entire foot off the top of the rail, because the suspension ran out of travel because the curve got so tight. The suspension was trying to keep all the wheels in contact with the rail, and it couldn't do it. It ran out of travel, and it just propagated forward, and all it could do was pick the wheel up. And so it was literally holding the inside wheel. I mean, it was a good 8-10 inches off the top of the rail. The wheel was up here. I've never seen anything like it. But that's what happens when you don't have proper ballast. Thankfully, proper ballast is very simple. You need crushed rock, is what the people in the rock industry want to call it. Not river rock, not smooth stones. You want jagged, I've been squished by mechanical processes and I've got lots of pointy edges that'll stab you rock. That kind. And you need a lot of it. And it needs to be tamped. And what that means is you basically need to smack the crap out of it so that it settles perfectly, and every little one of those edges is crabbed in on any other piece of ballast all the way, and all the way up to the ties and all the way around the ties. So you can see how I said those ties are square in profile, but you can't see the edges because the ballast is all the way up tight to the side now. And so at the museum, for the longest time, we were hand tamping, where you take a stick with a little with a little square on the end of it, and you smack it into the ground as hard as you can. And God help the track volunteers that did that, because, goodness, that sucks. Even for just a half-mile of railroad that we had, yeah, that's no fun. These days, there are actual mechanical tampers that basically, they see the tie, and then they have lots of little vibrational little hammers that come in on either side. They do their thing, and it squishes down the ballast and vibrates it into place such that it can't move anymore. You've maybe seen these. They're on-track equipment, typically yellow on the railroad. They look very cool, but that's what they're doing, is they're going and they're tamping the ballast down when they've got those little tendrils. It almost looks like an insect of some variety. But it's a really important thing to make sure that your track doesn't go anywhere. Equally important to that is proper grading and proper drainage. Because another problem that we faced here at this location was that the water was kind of pooling and collecting, and wet ground likes to move. and that does not help us run trains. And so we actually installed a French drain all the way down both sides, all the way down the cut, so that all the water would wash down along the side of the railroad, it wouldn't get absorbed into the ground, and then it would drain away from the railroad. And that way we could have nice, solid, dry grade for our big pile of nicely tamped ballast to then interface with our track. And all of that kept things solid as a rock, and even running this 150-ton steam locomotive around a very sharp curve on the railroad. Standard gauge railroaders are probably seeing this curve and going, good Lord. And it allowed us to do all that without issues again. Now, I was just talking a lot about gauge when I was talking about standard gauge railroaders, cringing at how sharp the curves are. So I think it's a good time now to talk about the measurements of railroad track, and that is the first one that you need to know, and that is gauge. What is gauge? Gauge, when we're talking about a railroad, is the distance between the rails that the train runs on. So the distance from this rail to this rail, or the distance from this rail to this rail. I've presented you with an interesting example because this is what's called dual gauge track, where there's two different gauges. Here we have 3-foot narrow gauge, which is a lot what I dealt with because I worked on railroads in Colorado. But we also have 56.5-inch standard gauge, or 4 foot 8.5 inches. But it's a lot easier to just say 56.5 inches. This is the standard that most of the world uses at this point, and is common. If you see an Amtrak train, you see BNSF, Norfolk Southern, whatever it is, that's what they're running, is that standard gauge, 56.5 inches. But in Colorado, we had lots of mountains, and we needed our trains to get around them, and we didn't want to pay a lot of money to make that happen, so we made them smaller, and we put them on smaller pieces of track with a smaller gauge so that we could do sharper curves without issue, and we had to blast less rock away until we then decided to basically toss standard gauge size locomotives onto the narrow gauge track in every dimension except for the height, because this locomotive is the width of a standard gauge engine easily. It's just not as tall as a standard gauge engine. Anyways, that's beside the point. But gauge is the distance between your rails, 36 and 56.5. How do you like that? Now, that's not always the case, though. Like anything in engineering terms, there's what we call a tolerance on the gauge, because you can't always keep it bullet perfect 36 inches or 56.5 inches. The trains are going to do stuff, the rail can bend, the rail can move, the ties can wear out, the spikes can get loose, all sorts of stuff, but we still need to run trains. So there's actually tolerances on this, and the specific tolerance of what is acceptable is entirely dependent on how fast you can run the train and the types of curves and everything, but 36 is what you shoot for. Sometimes it's 36.25, sometimes it's 36.5, sometimes maybe it's 36.75. It's getting a little out there. Same thing, standard gauge. Sometimes it's 57, sometimes it's 57.5. But if you're running a fast, high-speed operation, you need to be a lot closer to this. But you're allowed this tolerance because the wheels that the trains have are actually tapered in profile. So when you look at a wheel set on a train, it's not just flat, flange, flat. It's actually tapered so that it gets bigger as you go towards the flange. And so that means that typically the rails are riding somewhere in the middle, but as the train goes around a curve one way, it'll start to rock the one way until it hits the flange, or it goes the other way, it does the same thing. But it also means that if the rails are a little further out, you just ride a little further out on the taper and the locomotive sits down a little bit more. Or if it's a little bit narrow, it rides a little bit closer, which provides a problem as well. But you've got a couple inches here of play in these wheels, but obviously that gets extrapolated with how fast you may be operating your trains. So faster you run, the tighter the tolerance has to be. That just makes sense. So this is a good example picture of 3-rail dual gauge, where we have one common rail shared by both, then the 3-foot narrow gauge rail, and then the standard gauge rail over here. So both trains run on this outside rail, have one wheel on that, but narrow gauge trains use this rail, standard gauge trains use this rail. There's actually another kind of dual gauge rail that is common specifically at locomotive repair shops. And here we have a picture again of the roundhouse at the Colorado Railroad Museum with all 3 of my children They're not mine, but, you know, they're important to me. The 346, the 20, and the 491. But you can see here that we have 4-rail dual gauge, where you have standard gauge on the outside, and then you have narrow gauge on the inside. And the purpose of this is so that you could line up the couplers, so it's easy to move everything. You could potentially, you know, rather than adjusting for both distance, left and right, and height, now you just have to account for height, because narrow gauge couplers are lower down than standard gauge couplers. But that's a much easier problem to solve than, oh wait, is it left side bias or right side bias, 3-rail, what's going on? Even a lot of locomotives ended up with like a T-slot coupler, actually, where you could have the coupler down here, or up here, depending on what kind of cars it was shoving around, if it was in dual gauge territory, which makes things really complicated, but it's kind of neat. And you don't tend to see 4-rail narrow gauge because the railroad didn't want to pay for the 4th rail. Share that 1 rail. But at the shop, it makes a lot of sense to have the extra rail out there so that you can keep things centered up, everything's centered underneath the cranes, everything's centered over the pit in the case of 491, all that good stuff. So that is all about gauge. So the next really important thing to talk about in terms of railroad track is elevation, or more specifically, what the grade is doing. We talked about the grade as in the foundation ground that the track then sits upon, right? But what about the actual gradient of how steep the track is? How much elevation change does it get? This is the same for roads as it is for track, but grade is talking about rise over run, it's slope. It's algebra class all over again. You know how a lot of people joke about how they never had to do algebra since they left high school? Well, guess what? Some of us actually had to, and we enjoy it because we're nerds. Anyways, so as the track goes uphill or upgrade, we measure how far the track goes, the run, and how much height it increases, the rise. And then we use a ratio of the rise over run to come up with what the grade is. So for the folks in the UK with their railroad system, they typically would express this just explicitly as the ratio. So if in 100 feet, you went up 4 feet, you would have 4 in 100, which they would then be good mathematicians and equalize down to 1 in 25. And in the United States, we would take this and we would say, no, that's 4%, because we went 4 feet in 100. We went 4% of 100 feet up each 100 feet. And 4% is very steep for trains. The steepest mainline grades, typically that the railroads try to keep to these days, are in the 1.5 range. Obviously, there are some that are steeper, and many famous ones that are 4% or even more, even on standard gauge. But 4% ends up being kind of the end-all be-all for a lot of narrow gauge, right? That's the whole point, is we're running over mountains, so, you know, maybe we are okay with a little bit of steepness here and there, and we'll just tack an extra engine on when we need to. But at the end of the day, we're typically moving 15, 20 cars, not, you know, 200. So that's kind of why that is. But this is one kind of elevation that's very important. There's another kind of elevation that is perhaps even more important and more common. So imagine we had a curved bitted railroad. It's a sharp curve, and we wanted to run around it fast, but we couldn't without flying off the track. And we needed a hero to save us. What would the hero's name be? It would be Superelevation. Yes, he's not just elevation like we talked about, he is Superelevation. Okay, apologies, that was a stupid joke. But Superelevation, if we have a big left-hand turn like this, right? Superelevation is where we take our track and our grade and we bias it towards that side. Say that we set our reference point here. So if we say that this is 0, that is no elevation, that is the height of train, and we're going around this sharp curve, we might add a couple inches here. We might have 3 inches right here. So the outside rail of the curve over here is higher than the inside rail. And what does that get us? Well, that means that when we put a train on it, the whole train will kind of lean that way. And as the train is going around this sharp curve, physics is saying, I want to throw this train off and make it tip that way. But now we've countered physics by saying, rather than the weight going down towards the center of the train car as we normally have. Now the weight is going slightly counteracting that we want to fling you on the outside. It's the same thing why a lot of racetracks have banked corners. We can have a banked railroad turn. Now, it's not typically too much. 3 inches is a pretty decent amount of super elevation, but super elevated track is really common in standard gauge applications where things are running really quick. And it's actually really, really important for those. And it's what sets the speed limits for some trains, because the speed limit for how fast a train can run around a curve is entirely based on the unbalance requirement, which is talking about, okay, well, normally the center of mass of the train is smack dab in the center of the rails in straight track. But as we turn hard left, it wants to be thrown to the right, and we can counteract it a little bit with super elevation, but we can't let it go too far to the right as we turn left, right? At some point, the train will tip over, because we'll get too far past our normal center here. And so we cap it and say, well, you can't have any more than this. As you add super elevation, you know, perhaps normally, if you're going 79 miles an hour around this sharp curve, you'd be here. But because we added the elevation, well, guess what? You're actually only here. So you can run that speed. And one nifty thing is some really advanced high-speed trains, particularly in Europe, but some here in the States, will actually tilt. They have tilt technology, like the Talgo trains that Amtrak has, where they can take their normal train and they can adjust the suspension with some control and shift it so it tilts inwards so that it applies its own elevation as well, which further moves that inwards. And so that way they can run faster around the same curves as our conventional trains. And so that's what super elevation is all about. It's about mitigating how much force is trying to throw us off the railroad and make sure that it's not too much. And typically, actually, the unbalance requirement is based on passengers for passenger trains, because not only does the unbalance of the train as it goes around affect how much force is going there, if you're trying to walk down the aisle in the middle of the train, if you're trying to be flung out the window, that also doesn't help either. So it's actually typically a passenger comfort requirement before it is actually a safety we're going to tip over kind of requirement. And that provides you the safety factor towards that as well, because obviously we don't want to get too close to trains tipping over. We just talked a lot about curves, but how are curves calculated? Well, thanks to Trains Magazine for this brilliant demonstration of what it is. So we have to measure things in the real world, and we can't just exactly plop down a couple points saying that this is at this location, this is at this location, make it happen. Or at least not yet. I imagine with GPS we will get there. But what we do instead is we bring a 100-foot long piece of string or cord or whatever you have, and we can measure 2 points. If we know that the track passes through those 2 points in a circular arc, not in anything that changes the sharpness of the curve, we innately know its radius. And so we end up calling this the degree of curvature, and that's what we use on the railroad rather than the specific radius, because a lot of times it's really hard to find where the actual center itself is. And so we measure it this way, because a lot of times there'll be a lot of buildings or whatever on the way, or trees or what have you if you're building track from fresh back in the day. And so you'd need to know, okay, well, I can measure from here, boom, 100 foot, okay, this is the degree of curve that I'm going to go with. But in general, railroads like circular curves. We try to do circular curves for ease of things, but a lot of times things, particularly in faster applications, need to be a lot smoother because, transitioning in and out of things is important. And so a lot of times you'll have a curve where rather than being this perfect circle right here of the same constant degree of curvature or constant radius, well, you'll have a straight piece of track that eases in with what's called the spiral into a sharper curve, and then it'll ease out again on the backside. And so you will have what is called tangent track running straight in this portion, and you'll have the point of spiral right here where the track begins to spiral. And then at some point you will have the spiral to circular curve point, or the SC point. So we spiral in, we're increasing our degree of curvature or reducing the radius as we get closer. And in this region here, we have a constant radius This is all the same. So this is talking about it being a circle in here. And then again, we will have now a circle to spiral point on the back side, where we go back until we get back to tangent track once again. And that is the basis for most railroad track geometries. And so when you have this knowledge and couple it with the unbalanced requirement, you can figure out how fast your trains are going to be able to run around a particular section of railroad, which is how timetables are made. And I suppose at some point we should probably do a primer on timetables as well, if you're unfamiliar. So if you'd like to see that, let me know in the comments below. Okay, so we've talked a lot about the different pieces of track, the different components that build what track is, and then a lot of different ways to measure it. But what are the kinds of types of track? So there's a couple different types, and I thought this would be a good time to talk about them. So we've used this example several times of this piece of curve, and this is what we call at-grade ballasted track. What does that mean? It means that it is at a grade, or it has been graded, and it is at that height. It's not on a bridge up top, and it's not on a tunnel down below. It is at the height of the groundwork, and it is ballasted, which means that the track is being held in place by ballast, and we have ties and everything else that we talked about associated with that. There's also what we hinted at earlier with direct fixation track. And this is where, rather than using ties, the rails are directly fixated to the ground at a preset distance. These types of tracks typically need less maintenance because there's no ballast that needs to be replaced or tamped, and things are typically more rigid, but at the same time they're typically only seen in transit because the right-of-way cost is significant to pour this much concrete and use these many rail anchors. And this is a transit application with the electrified railroad, with some fun stuff in here that we will talk about at another time. The point of this track is that it is directly fixated to the ground, and the rails can't really move, as opposed to in ballasted track. The next kind of track we have is called embedded track. And embedded track is where the track is actually sunk into the ground. So you can see here, I had to zoom in quite a ways. This is the only picture I could find. I was looking at some flashing lights for a grade crossing, and the track happened to be in the background. So I try to pull all of my pictures from pictures that I've taken, A, to corroborate my experience, but B, also to not deal with any of the copyright fun stuff or permissions. But anyway, so this is track that is sunk into concrete. This concrete has been poured over top of it using forms. It's not panels of concrete that have been placed. Like typically at a railroad grade crossing, you will place prefabricated panels on ties. In this case, there may or may not be ties. The concrete is then poured over the top. It depends. Sometimes they'll use direct fixation track and pour over the top. Some places have used just the rails set into concrete and prayed, which it's not the best, but it has happened. And sometimes there are ties underneath as well. But when you pour the concrete over top, you can't get at it for maintenance. But this also gives kind of a neat rail profile that's really fun to see. So if you were to look at some embedded track like this, typically your rail profile, you have your foot, you have your web, you have your head, and then assuming that the open spot of the gauge is to the right, you then have the flangeway built right in with an extra arm like that to hold off the rest of the concrete. Sometimes it looks like that, sometimes it's built into the foot, it just depends. So the flange of the wheel can still clear when it goes, but that way they can pour the concrete all the way off to one side or another. So these are really unique rail profile that you'll see typically for trolleys, or again, a transit application, which is what this is. And the last kind of track we have to talk about is an interesting type of track that is only sometimes used depending on the exact application that you have, and that is panel track. And this is the real-life version of your model train set, where we have prefab sticks of track that you need to place, and you can haul them on trucks, as shown here, and take them to the job site and place the pieces down and do what you need to do. So sometimes these are used for special moves or temporary moves of equipment that are, like stuffed and mounted steam locomotives that are parked in a park or something and need to be moved. Sometimes it is a stopgap while track is being replaced or things are being changed. Track panels can be used for a lot of different things and placed into place really quickly rather than setting the ties individually, then welding rail in and all that stuff. So you can have some quick temporary track with track panels. And for the last thing in our video, we're going to talk about classes of track. And I'm shamelessly going to reference Wikipedia for this and provide my own guidance on top of it because there's not really a great way to draw the different kinds of track. So the Federal Railroad Administration, or the FRA, has requirements about what kinds of traffic and what speeds they can run over what kinds of track, and they will audit you based on those. And there's different maintenance standards and track standards involving how many anchors and tie plates and spikes you need and all that fun stuff on the different classes of track. And as the number gets bigger, the speed gets faster. That's all you really need to know. You have classes accepted, and then 1 through 9. So most track you see in service is usually hopefully like class 3, class 4, some of that stuff. But if it's out in an industry or somewhere local around town where they're not running very fast, it might be lower than that. But in the case of accepted track, freight trains are allowed at less than 10 mile an hour. And that's what we had at our mechanical shop as well. And I've spoken about this before. I used to work for BNSF at a mechanical facility, and yeah, we had a speed limit of 5, and we only moved locomotives. So we had some horrendous looking track that the guys were worried about, and the engineering team said that they couldn't come fix it because guess what? It was still okay for accepted track, and it would have been excess spending to fix the fact that we had like something like 15 or 16 ties in a row that were just roached. It looked awful. But hey, trains ran over it and it worked. It looked awful, but hey, nothing ever went in the dirt, knock on wood. So what are you going to do? That said, passengers not allowed on accepted track. Class 1 track, 10 mile an hour for freight, 15 for passenger. Passengers typically allowed faster speeds because the equipment is typically heavier, imparts less wear and movement on the rail. Class 2, 25 mile an hour, 30 mile an hour for passenger. Again, still not terribly common. A lot of tourist railroads are class 2 tracks. Sometimes they're class 1, but typically about class 2. Class 3, 40 mile an hour for freight, 60 mile an hour for passenger. Class 4 is very common, 60 mile an hour for freight, 80 mile an hour for passenger, because the regulations for what you need to do as far as grade crossings and some signaling things change at 80 miles an hour. So 80 miles an hour for passenger is more important than 80 miles an hour for freight in most considerations. So there's a lot of class 4 track out there. Class 5 allows freight up to 80 and passenger to 90, provided that the signaling does all its things it needs to do. So class 4 and 5 are kind of your bread and butter for the class 1 railroads, which means big railroad, because class railroad is different than class of track, because of course it is, because why wouldn't anything make any sense in the railroad? Anyway, but class 5, class 4 are the most common. Class 5, where, you've got a transcontinental freight line and you want that freight to run at 70 miles an hour, maybe 79 miles an hour, something like that, before you get these signal restrictions. So very, very common stuff out there. Class 6 is starting to get into high speed, 110 mile an hour. Class 7, 125 miles an hour is even higher speed, of course, which is most of what Amtrak's Northeast Corridor is. Class 8 is even faster than that at 160 miles an hour for both, but this gets a little challenging for us in the States because as soon as you go above 125 miles an hour, you cannot have any grade crossings. No flashing lights, no gates, no nothing. You can't have that. You have to have an exclusive alignment that cars and people can't get to. So fenced off, no grade crossings, track exclusive, because train going 125 plus miles an hour is cooking and will, seriously hurt some folks. So that's why, you don't see too much class 8 track, is because it's prohibitively expensive when you're talking about a country as large as ours. And class 9 track is for 220 miles an hour, and there's no actual built-in service class 9 track in the United States. And now all of Europe laughs at us at the fact that they have trains that run even faster than that and have in testing run way faster than that. So those are your classes of track in America. Okay, so that was a primer on track and what makes it up, so that we can eventually talk about the more fun and sexy things like interlockings and signals. Ooh. So, what did we talk about? Let's do a quick recap. We talked about track. It's what trains run on. It's made of rails, ties, spikes in the most common variety. Rails are made of a head at the top, a web in the middle, and a foot at the bottom. Rail used to come in different lengths. As time wore on, the lengths got longer and longer, and it made it easier and easier to install the track. Rail also comes in different weights, whereas the old weights per every 3 foot were quite low, like 30, 45, 55, that sort of weight per 3 foot. Now we have 115, 136 pounds every 3 foot rail. We have ties. Ties tie the rails together and hold them in place, and we have special devices to help us do that. We have tie plates that help distribute the force from the train to the tie, and they also help locate our spikes, and the spikes hold the rail and tie plate to the tie. The ties are typically made of wood. They're typically treated with creosote to make sure that they last a long time and also can accept the forces from the rail and the tie plates without wearing excessively. We also have rail anchors that prevent the rail from moving longitudinally down or up the track as the train imparts the force to it. And as well, in some applications, we also have rail clips instead of spikes, depending on the kind of railroad we have, because some ties and some applications use concrete rather than the wooden ties. When you have rails, you need to join them together. And back in the day, we had joint bars that had holes in them and rails that had holes in them that we would stuff bolts through and hold things together. And later, we ended up getting continuously welded rail, where we would weld the joints using thermite in a cool, flashy way to actually affix our rails so that we get a continuous head of rail so that the wheels never get the clickety-clack over the joints as they go across. But that said, we still do have these orange insulated joints for signaling applications, common across the railroad. We have the gauge of the rails, which is the distance between the rails, the most important measurement. We have standard gauge at 56.5 inches or 4 foot 8.5 inches, used by most of the world, and then sometimes we have narrow gauge, which is very common and dear to my heart. And for the Railroads Online players of you, if you found this video on YouTube and have never heard of Railroads Online, I'm a developer of that video game, which is why I make references to it. We have 36-inch gauge or 3-foot gauge track in that game. We also have grades. The railroad needs to run up hills, so we have grades that allow the trains to go up and down, measured in percent if you're in the States, or in a ratio if you're in other parts of the world. We also have other ways to measure what the track can do. We have superelevation, where we can raise one rail or the other to allow us to move faster through the same geometry, because we can lean the center of mass of the train into the force that's trying to fling it off of the tracks. And the last important unit of measure for a railroad is curvature, where we have degrees of curvature because we have to measure things in the real world, but you can calculate the radius out from that. And typically, if we have higher speed trackage, rather than just using a chunk of a circle, we will have a tangent straight piece of track, a spiraling in piece of track that goes from straight to the degree of curvature. Then we'll have a constant degree of curvature, constant circle, spiral back out, and then straight piece of track again. We have many different types of track using all these techniques and things that we've talked about. We have at-grade ballasted track like this, where the track is at the grade. It's not a bridge, it's not a tunnel, and it has ballast that holds it in place. We have direct fixation track, where the track is directly fixed to the ground, each rail individually, without even the use of cross ties. And then we also have embedded track, where the track is sunk into the ground and typically has an extra special rail profile to ensure that we can pour concrete but also maintain our flangeway. And then we also have a special use case panel piece of track that we can move around and place as we need to for construction purposes or other special movements. And then last but not least, we have many different classes of track that allow us to move our trains at different speeds based on what's appropriate for the railroad. Anyways, guys, I hope you guys enjoyed this primer on railroad track and what goes into it and some of the nomenclature about it. I know it's not the most interesting subject out there for those of you that are not civil engineers. I'm a mechanical engineer, and I frankly find track not that entertaining, but I'm really excited to talk about signals and interlockings and switches and special track work in the next 101 series. But this was really a necessary primer to make sure that everyone kind of understood some of the terms that we're going to talk about when we get in there, because switches and interlockings and signals get pretty complicated, and if you don't understand how tracks put together, then you're not going to be able to get there. So anyways, if you like this video, please click the like button. Please subscribe to the channel as well. And if you really like the channel, make sure you click the little bell, and it'll let you know whenever I'm uploading stuff. And I'm trying to crank out as many videos as I can. It's been a lot of fun these past couple weeks. So I hope you guys enjoyed this video. Thanks so much for watching once again.